Okay, so welcome back to this afternoon session, which will be on using some of the data that we showed you how to generate earlier to actually train machine learning models. So we're going to go through some machine learning models that were trained with this AFLOW data. Okay, let me do full screen. Okay. So I already showed how tools like the REST API. So yesterday evening, Marco went through the REST API and AFLOWs, showed you how you can access data in the AFLOW database, and showed you just how much data we have actually already calculated with AFLOW. So, however, each of these entries properties, so these 3 million or so entries that we have in our database, each one was calculated with DFT. And this can be quite computationally expensive. And so it's literally taking like decades to calculate that total amount of data. So what we want to do now is to use existing data to construct a model that can predict properties of materials with high accuracy, but with much less computationally demanding. So to use machine learning, train machine learning models on this data, and use this to accelerate materials discovery. So what we did was the following. We took the data for about 26,000 materials that are on aflow.org. So this was to train electronic properties. And we have about another, maybe like 3,000 to train thermomechanical properties. And we use this to train a gradient boosting decision trees machine learning model. And the predictions for this model are based on structural morphology and on elemental properties. So we use what's called, so to characterize the structure of the material, the structural morphology and the connectivity between the atoms, we use what was called a Voronoi tessellation. So basically for each atom, each pair of atoms, you draw a plane halfway between the atoms. So for every set of atoms, you draw these planes. Then each atom is going to be surrounded by a set of planes. So this forms what's called a Voronoi cell for each atom. And it's dividing up the material like this is what's called a Voronoi tessellation. And then the idea is that if two of these atoms share a Voronoi cell face, then they're considered to be connected. So sort of considered like as being bonded. So this gives you the sort of connectivity between the atoms. It's sort of a measure of how, relatively speaking, how close two atoms are, how much they interact with each other. So by looking at which atoms are connected, like which ones share a Voronoi face, you're able to draw, you're able to create a crystal graph describing the material. So the connected atoms form these, what they call these structured fragment descriptors. So the individual nodes of the graph are just the atoms. Edges, so bonds between atoms correspond to edges of the graph. Then when you've multiple edges together, you have path fragments of different lengths. You can also have different shape fragments, so polyhedron fragments, circular fragments, etc. Okay. Then for each of these nodes that are in the graph, each of these atoms, we decorate these nodes with elemental properties of the corresponding elements. So things like ionization potential, electronegativity, number of valence electrons, covalent radii, these sorts of common materials, fundamental materials of elements that really describe their chemical behavior. So then the way that it was trained on two sets of data. First, it was trained on electronic properties. So these are essentially the unique material. These were trained on the unique materials in the ICSD. So the first part of this was a classification model to determine whether the material was a metal or an insulator. If it's a metal, then it doesn't have a band gap. However, it's an insulator that does have a band gap. So then you predict the energy of the band gap using a regression model. Then for these other materials, these thermal and mechanical properties, it predicts, again, a set of regression models for things like bulk modulus, shear modulus, the body temperature, heat capacity, and so on. So one of the important things about these models is that they're only based on the crystal structure and then the fundamental properties of the elements that are well tabulated, so available in like textbooks and these sort of things. So the advantage of this is that you don't need any DFT calculation input. So literally the only thing you need to supply is the POSCAR file, something like a POSCAR file with the positions of the atoms and the lattice vectors, and then the list of elements themselves that are actually involved and which elements are on which sites. So once you have these models, once you build these models, you can do different types of things. One of the things you can do is analyze the partial dependence of the properties on different descriptors, or different fundamental properties of your input and of the material itself. So things like, for example, here we have the variation on the standard deviation of the bulk modulus from the average value versus the volume per atom. And you can see that as the volume per atom goes down, the bulk modulus goes up. And so we have a question in the chat. How do you decide? Okay, how did we decide that gradient boosting decision trees was the best model? I don't know that we necessarily did decide. I don't think that was decided a priori, as too much that was a relatively straightforward model that, like, at the time. So generally speaking, neural networks would probably give more accurate results, but you generally need to have, but they tend to converge. Basic neural networks tend to perform better the more data you have. Whereas if you have less data, things like random forests, gradient boosting decision trees tend to work somewhat better. So it was sort of an intermediate type of decision. I don't know if there was any super specific reason why they focused on, why the original focus was on decision trees. I don't know if you remember, Corey, you were probably involved in this even earlier than I was. Do you know if there's a specific reason they chose decision trees?
So, well, we did an earlier machine learning study, and we did partial least squares machine learning on that set, and we also did random forest. The random forest tends to be the most generalizable, and it's also it's pretty well integrated in terms of Python. So I think those are two of the reasons why we chose them. But otherwise, I mean, in general, you should be able to retrieve. I mean, assuming you have the right descriptors and you create the right fingerprints and fragments, you should be able to leverage other machine learning algorithms, and they should perform generally about the same.
That's generally one of the things that we find, is that what matters more is the quality of the features and descriptors that you use to describe the material itself, rather than the actual specific machine learning flavor that you end up using on the back end. That in general, most of them will converge to pretty much the same result. What really matters is how good your input data is, how reliable your input data is, and how good your descriptors are of actually like the type of features that whatever way you use to describe the structure of the material, the individual elemental properties you include, etc. They're really the important things.
There were also a few more technical reasons that we listed in the paper for why we chose specifically gradient boosting. The implementation that was in Python that we used, I think it's XGBoost is the one we used. It handles missing data very well. So there's also there's also some technical reasons why some implementations might be better than others. So, you know, I think there's a gradient boost in decision trees, and in some of the other imports in Python. There's some other packages that have GB decision trees, but the one that we used was it had some technical advantages as well.
Okay, thanks, Corey. Okay.
Yep.
Okay, so as I was saying, you can see that the bulk modulus tends to decrease with increasing volume per atom, and this is something that's already well known. It's not unexpected. You know, the further atoms are apart, the easier it's going to be to push them together in general. Here on the right, we have something that's a bit less expected. It's something we haven't really fully understood yet, and it may well be an artifact of the training data, is that the variation in the Debye temperature seems to depend quite strongly on the anisotropy of the cell. So cells that have much longer C lattice vectors than B lattice vectors seem to have much higher Debye temperatures. Again, this is something we don't really understand. It's something that was unexpected, that was thrown up by the model. And it's an example of where models can actually find things that you wouldn't necessarily expect in the data. So you can find these sort of patterns in the data that are kind of unintuitive, and that you might want to investigate further and see whether it's just an artifact or whether it's actually some new interesting design rule. Okay. Okay, so then we can also compare the predictions of the model with both density functional theory and with experimental data. So here we've taken our bulk modulus, our shear modulus, and our Debye temperature. On this axis here, we have the experimental data that's extracted from the literature. On this axis, we actually have the calculated data that was actually used as the training data for this model. And on this vertical axis here, we have the actual predictions made by the machine learning model. And you can see that all three, so the experimental data, the calculated data, and the predicted data, all lie very close to the same line. So they're all very similar to each other, particularly for the bulk and the shear moduli. For the Debye temperature, there's a bit more scatter, and you can see this in the difference in the R-squared values for the bulk and shear modulus versus the Debye temperature. Okay, so now to try and increase the availability of these models, make it easy for people to use so they don't have to worry about trying to install all the different dependencies. We've made them available online at aflow.org/ml, AFLOW-ML. So if you go to the aflow.org webpage and you click on this icon here, the AFLOW-ML icon, you will get to this page here. So this shows three different models. So the first one is the PLMF model, which I described already. Then there's two other models I'm not going to go into in detail. They were trained on other data other than AFLOW data. But so the first one is this, the second one here is this molar fragment descriptor, or MFD model, which is primarily for predicting vibrational free energies and entropies of materials. And then we have this AFLOW superconducting model, which is for predicting critical temperatures of materials. So to use this model, what you do is you paste your POSCAR here. And note that this is a slightly different version of the POSCAR than what we saw earlier. So before we were usually using the VASP4, so version 4 of VASP type POSCAR, which does not have this extra line here. So in VASP5, you have this extra line, which is basically just a list of elements in the order they appear down here. And in this case, in AFLOW, this will always be in alphabetical order. So in this case, we have our magnesium oxide rock salt structure. And here we add magnesium and we add oxygen. And then once we've copied and pasted our POSCAR of interest in here, we can click down here to run the prediction. Then this, after a little bit, like maybe 30 seconds or a minute or so, you'll get the results back for this prediction. So it'll give you, first of all, it'll give you some structural information. So in this case, it gives you the space group number. But then, sorry, whoops. It'll give you, first of all, whether it's a metal or an insulator. In this case, this material is an insulator with a band gap of 3.37 electron volts. Gives you an estimate of the energy per cell. And then we get the mechanical properties, so things like bulk modulus and shear modulus. Then we get thermal properties, so heat capacity per cell and per atom, Debye temperature, thermal expansion, and so on. So like I said, an important thing to note here is the difference between the two different types of POSCARs. So here, for example, for sodium chloride, here's the VASP version 4. So we have our, first of all, our title line, then our lattice constant multiplier. We have our lattice vectors. We have how many different types of each element we have. Then we have this line, whether it's fractional or Cartesian. And then we have the individual atom positions. And this version 5, now we have this extra line listing the different elements. And the reason why this is needed is because it needs to know which elements are on which site. Normally, when VASP is running, it gets this information from this POTCAR file because the elements will be listed, the different pseudopotentials will be listed in the right order. But here you're not actually passing any pseudopotential, so it doesn't know which elements it has. So you need to add this extra line so it knows which elements it's looking at. Yeah, so you need to add this line. Okay, so before we do the exercise, I'm just going to quickly run through an example so people can see how this works. Okay. So here's our AFLOW main page. If we go here to AFLOW-ML, we can bring it up here. So we'll have an example input here. But let's say we want to replace this with something else. So we can delete this. We can go to our page here. So if you go inside the OH AFLOW-ML /exercise/2 AFLOW-ML API, you can see that there's an example POSCAR here, POSCAR NGO. we can then copy and paste this. So this is already in version 5, so you can see it's got MGO here. So we copy. Okay, now we have to use the clipboard. Copy out of this, and hopefully this will work. Copy into here. Right, so now we have our postcard, and we just click run prediction, and we wait. And then you'll see this little circle come up here when it says it's running. And then you get the results pretty quickly. So if we scroll down further, you can also see that there's some calculation details. So this explains a little bit about the training data that was used to actually train the model itself. So you can see like the K-point grid, whether or not there was a plus U involved, etc. And this is pretty important for understanding the electronic band gap data, especially. Okay. So something else we can try, just to give you another example, is we can go to the prototype encyclopedia. We can search for a specific entry. For example, we can look inside. Let's look at the cubic space groups again. We can go and we can look for, let's say, the Heusler structures, which are 225, if I remember correctly. Heusler. So we can just, okay, in this case, I'll just take the default ones, but you can just substitute in different atoms and play around with lattice parameter and other things. We can copy this file. Hopefully this works. Paste it in here. Then we have to add in the extra line, the list of elements. And then we can try running this to see if it gives us anything interesting. And you'll see that it opens up an extra page here, so it doesn't actually remove this old one. And you can see now this one here, as you would expect for something that's aluminum, copper, and manganese, is a metal. And then you can see, so it doesn't have any band gap predicted, but you get the bulk modulus, shear modulus, and then thermal properties, etc. You can see this does not have any U effect. You know, U is used, although there's a U used for the d orbitals. Yeah. And you can see also which pseudo potentials were used in the training the model. Okay, with that, let's take a look at these examples. Let's get you started. So here, first one is to convert the Heusler structure postcard you decorated in session 4 from VAST4 to VAST5. So either if you have this still from day 2, you can take the postcard you generated. Otherwise, you can just generate a new one. It's very straightforward to do if you remember the exercise from yesterday. So I'll just do it now as an example, just in case people don't have it. Yeah, so I'll just show you using macros example. You can either convert or you can, so I'll do both ways just to show people how to do proto equals A2BC. So let's look at the actual on the prototype. A2BC, well, this is AB2C because we have 2 copies. But we can play around with the structure. And let's go C at 16. Let's go to 5. And then I have ACB. So let's see this. Okay, I'm having this issue with them. Sluggish connection. give it a second to start up. But I'll just go through the rest of the exercises while we're waiting for this. Okay, so then you take this postcard file. You can also do it just what I just did now. So go online to the AFLOW prototypes page and copy and paste generate the postcard that way and copy it into the PLMF model application. And then look at the wire bulk and shear moduli. So then you would take the same structure. We run the MFD model and see what properties it gives. And then finally, we take the chemical formula for whatever material whatever chemical formula you selected to decorate this with, and then run the ASC model on it. So what is the superconducting temperature for this composition? So just to clarify that bit, when you go to this model, so this will take, again, a postcard file, but this last one here, instead of taking the postcard file, it literally just takes the chemical formula. Okay, so I think with that, we can probably go into our breakout rooms. And okay, so I've taken the Heusler prototype from the online encyclopedia. I've decorated. I'm just taking the default decoration here of aluminum, copper, and manganese. So I'm going to copy and paste this into the AFLOW-ML, and I'm going to add this line. And I'm going to run prediction. Okay, so couple of other things you can see here. You also, as well as the postcard, you also have an option of loading a quantum espresso structure file. There you can see the output we get. So it's pretty quick. It's a metal, so there's no band gap. We have bulk and shear modulus values, and then various thermal properties, etc. Okay, so now I'm just going to copy this. So now we're going to do the molar fragment descriptor model. And you can see that this is a somewhat simpler model. And it gives the results much, much quicker. It's almost instantaneous. And it only gives 3 parameters, so the heat capacity, vibrational free energy, and vibrational entropy. And this was a model that was actually, I think it was actually trained on experimental data. And finally, there's the superconductor. In this case, AlCu2, 2, and N. So we put in the chemical formula, we run the prediction. Again, this takes a little bit longer to run. But again, we get that basically it's below 5 Kelvin, below 10 Kelvin. So it's essentially, it's not a superconductor. Which again would be what we would expect. Okay. So that's the online API, so the interactive one that's that you can use by hand. But what happens if you want to use this programmatically? What happens if you want to incorporate this into some kind of a materials design workflow, or if you have a data set, maybe a few dozen postcards or something you want to do, and you don't want to copy and paste each one in by hand, where you actually might want to use a script, you might want to use some kind of programmatic interface or an API. So that's what we wanted to do. So we designed this AFLOW-ML API. So this is basically, it's the same principle as what we had for the online page, except this time we're actually exposing underneath so you're basically able to upload a postcard programmatically and retrieve the predictions. That actually have to go through the actual website itself. So here we have our postcard file or some other geometry file. Mostly I think it just works for postcard for the moment. We can post it to this endpoint. So depending on which version of the model you're using, /prediction. And this will give you what's called a task object back. So this is basically a JSON file with the task ID. Then you have this endpoint, which you formulate by including in this task ID number. So you submit this endpoint request to this endpoint to get the results. And then you'll get what's called a status object, which will either tell you that it's the prediction has finished successfully, in which case you get your data, or it's still pending, or there's a failure, or there's a problem. If it's still pending, you basically have to query again a few seconds later until it's done. There's also an AFLOW-ML API client if you're interested. You can go and download this online. I'm not really going to go through this during this particular workshop. Okay, so I just want to give you an example of where we have used this kind of API naturally in the materials design project. So this was, we were using the, trying to discover new super hard carbon bases, and you can read more about it in this publication down here. So the MBJ Computational Materials, volume 5, page 80, article 89. So the idea here was that we integrated this PLMF model with this genetic algorithm code XDOT, which was developed by our collaborators in SUNY Buffalo to discover new super hard carbon bases. So the way this works is that we start from a set of what are sort of known carbon prototypes. They did some calculations to get the formation entropies of these to see what the thermodynamic stability was, and then to get the mechanical properties, they would feed this structure into our ML API. They get back the bulk modulus, shear modulus, and so on. From that, they can estimate the hardness of the material. So then they say, okay, which materials have both a good combination of thermodynamic stability and high hardness. They take those materials and then they sort of combine them together using this genetic algorithm to make new types of structures. And then they repeat the process. They select which ones of those new structures are the hardest. They combine bits of them to make new structures again, and so on. They try and so this sort of genetic evolution to find which ones are potentially harder than the existing known materials. So here you can see sort of the distribution. Here you have down here you have graphite-like materials. Up here was diamond-like. And here in this corner, here, this diamond-like materials, you can see this, they have this both combination of reasonably low energy. So this is a good thermodynamically stable on this axis. You want to be as further here as possible, and as hard as possible you want to be up here. So this corner here is the ones that are best. And the material that was actually most successful, I believe, was this one down here. So just as a comparison with this model tends to somewhat underestimate the hardness. We were getting values around 75 GPa for carbon diamond. So this is predictably slightly harder than carbon diamond. And you can see from this tiling what the structure is. So you see these blue patches here, these basically correspond to diamond type structures, while this yellow and green is what's called lanzolite, which is sort of a hexagonal analog of diamond. So it's this, so the hardest structure seems to be some sort of combination of the two, both diamond and then this lanzolite structure, which is this combination of diamond. So this gives you an idea of how you can actually use this model in machine learning workflows. So how do you actually access the data? So, okay, here I'm going to go through step by step, and then later on I'll show you how to combine all this together in a Python script. So the first thing to do is to take your VASP5 postcard and you submit it to your prediction endpoint with CERL. And one thing to notice here is this version number isn't actually necessary. This version 1.0 will soon be deprecated and we're switching to version 1.1. But if you leave out this versioning altogether, you can actually get, you should still be able to get the result, and it should go directly to whatever the most recent version is. So then this gives you back this task object, which is a JSON object, which looks like this. So here we have the task ID, and this is the results endpoint that we have to query. So eventually, instead of this prediction, we replace this prediction here with prediction/result and so on. And oh yeah, so we replace the PLMF/prediction with this prediction/result and then this task ID number, and this will send you back the results object. And a results object looks something like this. This is an example of a successful results object for the PLMF. So you can see the status here is successful. You can see the citation. So this is for the PLMF model. This is this Nature Communications paper describing this model. And then you get things like the prediction for the bulk modulus, the shear modulus, the by temperature, the electronic band gap type, and so on. And also it records which model you were using. So I'm just going to go through one example here so you can see what it actually looks like in practice. So let me go back to the interactive session. So here I have my example postcard of MGO. And you can see here that this is already converted to last version 5, where we have this extra line here. Okay, so now we want to do CURL. Let's go back up here. So we've got http://aflow.org/API. http:// aflow.org/ /API/AFLOW-ML. Okay, and then I have to, yeah, so I'm missing PLMF. So this is where I tell us, so PLMF here tells it which type of model I want, whether it's this one or the MFD or the superconductor model. And I have minus data, URL and code. And then I have file at pascar.ngo. Okay, so I do this.
I think capital.
There's a typo. Yeah, there's a typo. Okay. There. Okay, so I had a typo in the name of the file. So then I can retrieve the data from the endpoint, v1.0. Okay, so here's the model, here's the results itself. Again, it says success, and here's our prediction, predicted values. So just to show you, you can also remove this version number. That should also work. Yeah, so you get an endpoint. Go all the way back here. So this, copy it here. And we get our result. So yeah, so this version number is, if you want to specify a specific version, you can, but it's not actually necessary. Okay, so this is somewhat cumbersome. You're still having to do a lot of work by hand, and it would not be fun if you wanted to do a large set of different ones. So you can also write a Python script that will actually automate this. So you can imagine writing this Python script so that it loops over a large number of different postcards as well. Or it could be something that's built into some kind of materials design workflow. Okay, so there's a few important things here. One thing we do is we have this import sleep. So this allows us to wait. So if we get something that's, if it doesn't respond right away with the completed with a successful prediction, that it waits 10 seconds and then we'll requery, see if it's finished. So here's the server. Again, this version number is not necessary, so you can drop that if you want, and it will then default to querying whatever is the most recent version of the model. Here's our PLMF. Here we're specifying the PLMF model. So if you want to query a different model, again, you can change this value. Here, this encodes the postcar, so it reads. So here, in this case, the postcar is named postcar. If you wanted to point to the, for example, the MGO postcar that I have inside, you would put in whatever the name of that file is, so postcar.mgo. Or you can select whatever name you want for the postcar, as long as you have the correct name in here that matches the name that's actually of the file, that's of the actual file. So here, so this creates the URL that it queries, but then this is this is where it retrieves the actual task object. So it opens it, converts, so reads the, extracts the JSON, turns it into a dictionary, Python dictionary, reads the task.json value, so this results._endpoint value, and this then it builds the URL to query to get the results. Okay, so now that we have the results URL that it knows to query, it will select this, or it basically does another request to retrieve this status or results object. It then checks what this status value is. If it's pending, it sleeps for 10 seconds and then continues, and then it will basically go back up here and then re-download the status object to see if it's finished or not. Same thing if it's started. If there's a failure, so if there's some kind of problem with the prediction, so maybe your postcard isn't formatted properly, for example, it prints that there's an error. And then finally, if it's actually successful, it's finished properly, prints out here we print out the results. And here you can edit this to print out different values, or you can extract a specific value and use it in the workflow, etc. Okay, so now we're going to do another set of exercises. So in this case, we take again the postcard, the VAS5 Heusler structure postcard from the previous exercise. So either you can generate a new one, or you can take the one from the previous exercise if you still have it, or you can download it from generate using the online prototype encyclopedia. So then you should use this AFLOW-ML API script that should be inside your directory to then run the machine learning application on this postcard, and then to print out whether the material is a metal or an insulator. If it's an insulator, you can print it on there. So then second thing is to modify the script again to run, instead of running the PLMF model, you run the MFD model. Okay, and now the last one is a little bit more complicated. It combines this ML API with some work the things you learned yesterday about using AFLOW. So this shows you how to combine the different parts of AFLOW to try and solve something that's a bit more complicated. So the idea is here to find an entry in the molybdenum titanium alloy system with the lowest formation enthalpy per atom. So then you download this relaxed structure. So to download the postcard, convert it to FAST5 format, and use the AFLOW-ML API to find the bulk and shear moduli for this system. So this is something that's might be a more realistic thing as to what you might actually be trying to do in practice. So you might want to say for a certain alloy system, you might want to find the ones that are the most stable entries or something like this, and then see what the bulk and shear moduli of these are. Okay, so let me just do a quick example before we go into the breakout rooms, just to remind you how to do a few of these things. So first, one of the things we want to do is to retrieve this FAST5 postcard. If you don't have it, you can regenerate it. The easiest way to do this is like this. So I was showing this a little bit earlier, but let's see if I still have it. Yeah. Okay, so if you use this command here, so aflow --proto a2bc cf16 _225 c _a b dot ABC, so this gives you the order, aluminum, copper, manganese, or you can basically change this to have a different order if you want. Params equals -1 rescales the volume automatically, and then we have aflow --fast5 converts it to fast5, and then we want to write it to a postcard file. So let's just keep it as postcard, and then we do t postcard. I should write out the results. So let's see if now we have our postcard file. Yeah, and this is in fast5 with this extra line here. Okay, so if we want to try the exercises now, if we want to go into our breakout rooms again. And then this is the last set of exercises for this session. Okay, let me stop sharing. I'll click the thanks. The screen. Okay, So here's the questions we had. First question is to take this postcard from a previous exercise and use the ML API script to print whether it's a material or is a metal or an insulator, and if it is an insulator, to print the band gap. So in this case, we do postcard. Here you can see I have the VAST5 version of this Heusler postcard, where here I have the 3 elements. If I look inside, I think it's this old version. Inside this. So here, instead of just printing out the results.json file, we print out the EGAP, we check if the EGAP type is insulator. If it is, we write out the band gap. Otherwise, we write that it's metallic. You notice also I've removed this version here, so because we don't need that, so we can just see how it works, and it'll automatically redirect to the most recent version. And here we're using the PLMF model. So we hit Python, AFLOW, then we run, then we wait a few seconds. Now we get the results. So successful prediction, and you see that it's metallic. Okay, so we can also do this for this other model. So here, instead of PLMF, we're using MFD. And here we're just going to print out everything to see what it says. Again, for the same. Okay, so here's a successful prediction. And then for the last one, we're going to do a search. Here we go. So we want to look for molybdenum. So we have molybdenum and titanium, so MOTI. Number of species is 2. We select a display so that we look for thermodynamic properties. We select formation entropy per atom. Okay, let's go this one. Formation entropy per atom. And then we do our search over the entire AFLOW data. And here we're searching all of AFLOW. Okay, then we click here on these 2 arrows to sort. So we click down, we click there. So this is the one with the lowest formation entropy per atom. So if we scroll down to the bottom of this page, entry page, we can find our downloadable file. Then we can copy this const char. So this is the relaxed structure. We can copy it back into our, well, we have to go through our clipboard. Then we want to copy this. And then we want to paste it here. Then we're just going to run the, I'm not going to go through the very last part. I'm just going to run the PLMF model for this. So here we're going to change the postcard .moti, PLMF, save, and then we can run. So you can see. Okay, and here we get the results back, and here we can see our bulk modulus and our shear modulus. So you can imagine doing this with AFLOW. So you could incorporate the AFLOW search into your machine learning script, and you could then search for various different things, download the postcar, feed the postcar into the machine learning model, and then extract the predictions for things like bulk or shear modules that might not be in the database. Okay, so with that, I think we can wrap up this session, and we can take another short break, and we come back here at 4 p.m. I think it's going to be David Hicks is going to be doing prototypes.